Yeah. Hi, everyone. Thanks for the introduction. I'm very happy to be here. I'm the SGLang lead on the open source development. I'm also a member of technical staff from XAI, where we use SGLang for large-scale production serving running on AMD GPUs. So in this talk, here is the outline. So first, I will give a high-level overview of the SGLang project, and then I will share two of our recent technical highlights where we do large-scale prefill-decode disaggregation and large-scale expert parallelism. Because I cannot share too much confidential information from XI, so these two technical highlights are mostly covering the open source development. And lastly, I will share about our open source community and the roadmap. So what is SGLang? It is a fast inference engine for large language models and vision language models. It provides state-of-the-art performance for all major open-weight models like DeepSeek, Llama, and Qwen. And at XAI, we use it to serve the production and research workloads for our in-house Grok models. We run reinforcement learning with it. And if you go to grok.com today, you can chat with the model, generate images, and part of the traffic is actually served by AMD GPUs. Here I want to give a high-level brief overview of the history of this project because it's still a fairly young project. So last year, our focus is to provide fast inference for agentic workflows. So we propose a lot of novel techniques like the zero overhead CPU scheduler, radix tree-based prefix caching, and some faster structured decoding, and all common optimizations from other frameworks. And January this year, when the DeepSeek V3R1 came out, we actually collaborated with both the DeepSeek team and AMD team to provide day zero support for these models running with specific MLA optimizations and native FPA block-wise quantization on AMD GPUs. And then just last month, we also provide the first open source implementation to support large-scale expert parallelism with prefill-decode disaggregation for DeepSeek models. So by doing this, we can almost reproduce the performance and the throughput number from the official DeepSeek blog post. And this is the first real large-scale open source implementation running on over 100 GPUs. And today, SGLang becomes one of the dominant solutions for inference on AMD GPUs. And it's the default inference engine for many companies running over 100K GPUs worldwide from XAI and many other companies. So, and then I will go into the technical highlights. The first one is efficient design and implementation of prefill and decode disaggregation. So before the prefill and before the PD disaggregation, people do the normal non-disaggregated way of deployment, but it has several issues. I will list a few of them. So first, I'll call it prefill interruption. So because if you have a single engine, it runs both prefill and decode, and then they will interfere with each other. Let's say you are running a decode batch, and in the middle, if you have a new request coming, the engine has to switch to running the prefill for that request. If that request is super long, for example, 100K prompt, you have to run tens of seconds. And in these tens of seconds, the whole decoding batch has to be paused. So all the user in the middle of streaming, they will feel 10 seconds of delay. So this is very bad user experience and will cause very bad P99 tail latency. And the second one is DP attention imbalance. DP attention here means data parallelism for attention. It's a kind of parallelism strategy. And if you run this parallelism strategy and without prefill-decode disaggregation, then different TP ranks, they will actually run different phase. Some DP rank run on prefill, some the other DP ranks run decode. And when you combine them, they have to wait each other after every layer. And this creates a huge imbalance and increase the latency, so very inefficient. And the last reason is very similar to the second one, is some communication kernels, especially for expert parallelism, where you have different dispatch mode for these kernels. and one mode is optimal for prefill, and the other mode is optimal for decode. If you don't disaggregate, you have to only choose one mode and make the other case unoptimal. So to solve these issues, prefill and decode disaggregation almost become necessary for large-scale deployment. So here we show the high-level architecture where you have a group of prefill instance and a group of decode instance, and then you have a load balancer in the middle to orchestrate the two groups. When a request comes in, the load balancer is the entry point, and then the load balancer picks one prefill and picks one decode, and then pairs them, and then bootstrap the KV cache transfer among them. So in our design, we have a single load balancer to make it work for both prefill and decode, and then the KV cache transfer is non-blocking, and we support RDMA-based transfer for maximum bandwidth. And SGLang provides a nice abstraction for integrating various backends such as Mooncake, Nixel, and any of your in-house transfer backends. And here we show a simple protocol of how that works. So first, you have one prefill and one decode. The load balancer will choose a pair of two engines based on some load balancing strategy like list of requests or list of memory usage. And then they do a handshake to make sure they are all alive. And then they init a sender and a receiver. So on the decode worker, it pre-allocates a range of KV cache for receiving the KV cache, and then notify the prefill instance the decode memory allocation is ready. And then the prefill instance will run the forward, and then in the meanwhile, do the KV cache transfer at the same time and overlap the prefill and the KV cache transfer. And after that, the decode instance gets the KV cache and then run the decode forward. So this will finish one request. Okay, that's PD disaggregation. So after this PD disaggregation, we can solve all the issues and then enable flexible parallelism strategy. We can use different parallelism for prefill and decode and maximize the efficiency. So then I will jump into the next part, large-scale expert parallelism. And we use our own implementation to reproduce the performance from DeepSeek's official blog post and reproduce their high throughput, very efficient deployment strategy. So for DeepSeek model, it's a very big model, and it's also a very sparse model. It has 256 experts, and the total number of parameter is over 600 billion. So it's kind of counterintuitive. If you use more GPU to run this model, it actually becomes more efficient. If you use like 1 or 2 GPU to run this model, you don't have enough room for KV cache, so you can only run a very small batch size. But if you have maybe 100 GPU to run this model, you can actually amortize the weights. You can share the weights across many different GPUs and balance them well, and then you can run at a crazy high batch size, and you do some smart overlap to reduce all the to hide all the communication overhead. So it actually becomes very efficient. And in order to achieve this, we need some advanced parallelism strategy. So here we'll mostly talk about how to parallelize that. So for the DeepSeek model, it has 64 layers. The first 3 layers, they are dense, normal dense MLP or FFN layers. And we use some different parallelism strategy for them. You can look at this figure. We have 4 batteries, which represent 4 GPUs. And then first they go to the attention layer. We use data parallelism, DP attention, to parallelize that. And then go to the first 3 dense MLP layers. We also use data parallelism. The conventional way is to use tensor parallelism, but we use data parallelism here because for these 3 small layers, actually we find data parallelism actually performs better because of several reasons, like we can avoid the fragmentation, the data parallelism, the tensor parallelism splitting on large hidden dimension. And also for tensor parallelism, you need to aggregate and or reduce the activation from all the different GPUs. This creates a huge intermediate buffer. If you do data parallelism, you can avoid this buffer. And also tensor parallelism incurs more communication. It requires 2 OR reduce, but for data parallelism, you only need 1 reduce scatter and one OR gather. So this all this reason come up together, we pick data parallelism for the first 3 layers. And then after the first 3 layers, the following 60 layers, they are MOE layer, which is even more challenging. So if you look at this figure, let's say we have 4 devices here. We first run attention layer. We also use data parallelism for attention because it's MLA and we don't want to duplicate KV cache. And then we are going to the mixture of expert layers, where it's the interesting part. We first do a dispatch to dispatch the token to the corresponding experts. And then the green boxes running the different experts in expert parallelism. And finally, we have a deep EP combine to reshuffle the tokens and then go into the next layer. So in order to make this kind of parallelism efficient, we also need to carefully design a lot of components. So first, expert weights, we shard them so we can amortize the weight and has a huge enough memory for KV cache so we can run large batch size. And then the deep EP combine and deep EP dispatch actually is a lot of communication, although it's much less than other parallelism, but still a lot of communication. So we have to carefully design some pipeline to overlap the computation and the communication and hide the communication cost. And finally, for different experts, it's very common that you will see a huge imbalance among the expert distribution. So you need to design a careful load balancing to balance the token among different experts. I will talk them in details. So yeah, one major thing we need to do is to overlap the communication cost. So what we did is, like we learned from DeepSeek blog, we do the 2-batch overlap strategy. So we have, if you have a single forward batch, we logically split them into 2 batches, and that's 1 batch run compute, another batch run communication, and then they can be perfectly overlapped. So we hide all the communication cost. So you can see here, the yellow boxes are 1 batch, and the green boxes is the other batch. And then on the CPU, we carefully launch them and synchronize them with a correct signal, and then and the stream binding. And then you can see when the computation stream is running attention, the communication stream is running expert parallelism dispatch. And after that, the computation stream is running MLP layer for another batch, and then the communication stream is running expert dispatch for another batch. So we interleave them to resolve the dependency while also fully utilizing both the compute and the communication resources. To make this kind of schedule more overlap, actually in SGLang we also did something like more systematic. We build a nice abstraction which allow you to easily tune the pipeline. So then, for example, here in this code, you can define the operation is forward dispatch MLP combine, and then there is some yield operation allow you to synchronize between different streams. So by providing this nice abstraction, you can actually easily tune the 2-batch overlap strategy for different hardware, different cluster size, and different models, different workloads. Yeah, it is very flexible. Actually, we use this strategy to do it for DeepSeek and Qwen, and we tune it for different clusters. And then finally, I want to show some end-to-end benchmark results. So here, we want to show by doing large-scale expert parallelism and prefill-decode disaggregation, you can achieve 3x higher prefill throughput and 5x higher decode throughput compared to a normal pure tensor parallelism strategy. So here in this figure, we compare both prefill and decode. And if you look at prefill, the left one, which is a prefill figure, and you can see we test on different input lengths and a different parallelism strategy. We compare our expert parallelism 32 versus tensor parallelism 16. And also we compare the throughput achieved with SGLang system to the DeepSeek official blog post profile. And we can see SGLang, the open source implementation, can almost fully reproduce the low cost claimed from the DeepSeek blog. So right now, if you can deploy the whole system on your own local cluster, actually you can also achieve a very low cost. And we did some calculation. It is almost 5x cheaper than DeepSeek's API cost, although DeepSeek's API is already very cheap. And lastly, I want to share our open source community and some development roadmap. So SGLang has been used and adopted and supported by a large number of companies, and we collaborate with AMD very closely. AMD provides great support. They contribute features and test coverage, and we all develop in a very open and a collaborative way. So special thanks to some AMD contributors. And in terms of roadmap, as we already shared, we have some prototype for Prefill-Decode Disaggregation and expert parallelism. So in the next few months, we will make them all production ready, fully compatible with each other, compatible with each feature. And then we also start to heavily invest more on making all of these features, not only for production serving, but also for reinforcement and training. So we collaborate with multiple IL teams to integrate SGLang and all these organizations for the rollout in their IL training. And we'll continue to do day zero support for all the upcoming state-of-the-art open models. And in terms of AMD collaboration, we also make all the features available on AMD GPUs. And we not only do the common organization, but also we will integrate a lot of AMD optimized specific libraries, such as ATER and Quark. You also learn more about ATER in the following talks. And we'll continue to improve model accuracy, CI tests. If you are interested in our community, you can join our bi-weekly online development meeting, and we're interested to hearing your business cases. So yeah, that's all of my talk. You're welcome to check out the code. It's open source at GitHub, and you are welcome to join our Slack and bi-weekly dev meetings. Thank you, everyone.
Hey, Lianmin, thank you for the great talk. Check. Okay. Can I ask a quick question, Lianmin? So I think that distributed inference is super exciting, right? I mean, DeepSeek showed significant speed up, and I'm very excited that SGLang was able to, I mean, like you said, the very first open source to reproduce that, and probably beyond. Do you see it applies to more models? I mean, my impression is sparse MOEs and that is effective, but do you see more and more models gets that kind of multiplier speed up using distributed inference?
Yeah, sure. I think it will definitely apply to more models. So I think DeepSeek is a very advanced design. So in the previous generation, a lot of people still doing dense model, and then DeepSeek first show a large-scale expert MOE model, and also it's more sparse. So previously, people do 8 experts and choose 2. But DeepSeek, they do 256 experts and choose 8. So it's very sparse. I think it kind of mimic the human brain design. So I think this kind of expert sparse model is a general trend, and people will try to explore. Another big reason is previously, we don't have this kind of system support. So when people like the model developers, they are afraid to develop this kind of model. But now we show actually we can co-design a system to make them very efficient. So the model developers, they actually have more freedom to design even crazy models. And then the model and the system, they co-evolve. And in the future, I think we want larger models and distributed inference. And it's kind of intuitive. Like the larger your model is, the more GPU you have, actually you can be more efficient. So that's I think a general trend.
Hello, just a quick question. Can you elaborate a little bit on expert parallelism, and how do you deal with latency of your overflowing to other region? How do you distribute the model?
It's a question about how we distribute the expert and how we handle the latency requirement. Yeah, I think for expert, for example, if there are 250 experts and we maybe use like 100 GPUs, so first we evenly share the experts across the GPUs, but there are some imbalance, right? So for some hot or popular experts, we also duplicate a few copies, and then we run a load balancer to balance the distribution. And then we also have to periodically update the sharding strategy to fit in the new traffic pattern. So this is how we handle the expert sharding and the load balance. And for latency, I think that's a more challenging problem, because if you do all this large scale and you have a lot of communication, sometimes it's hard to hide the latency. I think here the most focus is on high throughput while maintaining acceptable latency. For example, human read speed is 20 to 30 tokens per second. If you are reaching this speed, then you are good for normal chat applications. And so, for the current setup, it actually can match this minimum speed very easily. And then if you still don't meet the latency requirement, you can add a little bit of speculative decoding to greatly reduce the latency.
Hi, Lianmin. I'm interested about your implementation of the two-batch overlap. And as far as I know, I think there is also similar communication overhead in other parallelism strategies like TP. We need to do to reduce. So do you implement it, or do you plan to use a two-batch overlap to hide the communication overhead of TP?
Yeah, that's a great question. Yeah, I think a similar strategy can be used for tensor parallelism as well. Although for tensor parallelism, we may have even more like alternative solutions. And for this one, because expert parallelism, it has less communication than tensor parallelism. So if we do tensor parallelism at this large scale, like we cannot even hide them because the communication cost is so large. Okay. Yeah. I think. Yeah. Thanks.